Welcome to this explainer. Okay, today we are going to completely flip how you look at our home galaxy, the Milky Way. Get ready to zoom out, and I mean way out, as we uncover this massive, invisible structure that actually surrounds us all. It's a wild feature shared by spiral, elliptical, and even dwarf galaxies all across the universe.
So, let's dive right into it. When you think of the Milky Way, what immediately pops into your head? You're probably picturing this gorgeous, flat, spinning plate of stars, right? Complete with that glowing central bulge and the sweeping spiral arms. And sure, that's the classic image. But what if I told you that glowing, flat disk is just a tiny fraction of the whole shebang? It turns out that glowing disk is actually encased inside something much, much bigger.
And that brings us to exactly what we're talking about today, the galactic halo. By definition, it's this extended, roughly spherical component of our galaxy stretching way beyond the visible disk. Now, you might be wondering, is it just empty space? Not at all. It contains ancient stars, incredibly hot plasma, and immense amounts of dark matter. Basically, our flat disk is sitting inside this massive, invisible dome.
Here is our roadmap for today. We'll start with Beyond the Galactic Disk, then move to Anatomy of the Halo, Relics of Galactic Cannibalism, the Dark Matter Scaffold, and finally, Decoding the Milky Way.
All right, let's jump into Section 1, Beyond the Galactic Disk.
Now, what's really fascinating here is the extreme contrast between these two environments. The galactic disk is flat, packed with relatively cold gas, buzzing with active star formation, and it spins quite fast. But look at the galactic halo. It's a massive spherical shape, the stars out there are incredibly sparse, and they're actually among the oldest known stars in the universe. We're talking mostly over 12 billion years old. That's because they formed during the very earliest stages of galaxy evolution, way before the central disk even settled into place. There is zero new star formation happening out there anymore, and its rotation is exceptionally slow or sometimes just completely chaotic. Honestly, it's kind of like comparing a bustling modern metropolis to an ancient, sprawling, quiet desert.
Moving right along to Section 2, Anatomy of the Halo. So, what is this vast sphere actually made of? Well, it breaks down into three wildly different components. First up, this stellar halo. This only holds about 1% of the galaxy's total stellar mass, and it's made up of isolated, metal-poor field stars and ancient globular clusters. These clusters are basically orbiting time capsules that tell us exactly how our galaxy formed. Second, there's the galactic corona, also known as the circumgalactic medium, which is this vast reservoir of hot, diffuse plasma. And third, the dark matter halo. This acts as the massive, invisible gravitational skeleton holding the whole thing together. Let's zoom in on that first component, the stars.
You know, the stellar halo isn't just one uniform cloud of stars. It's actually divided into two distinct overlapping regions. The inner halo has this modest prograde rotation, meaning it spins in the exact same direction as the rest of the galaxy. And it has higher metallicity, so more heavy elements forged by previous generations of stars. But the outer halo, it has a net retrograde rotation. It literally spins backwards, and its metallicity is only a third of the inner halo. For astronomers, this points to fundamentally different origins. We're talking dissipational mergers for the inner halo, where gas collided and made new stars, versus dissipation-less mergers for the outer halo, where older star clusters were just swallowed whole without triggering any new star birth. But hey, stars are just a tiny, tiny fraction of what's out there.
2 million. That is the temperature in degrees Kelvin of the gaseous corona surrounding our galaxy. Just to put that into perspective, that is a few hundred times hotter than the surface of the sun. This vast circumgalactic medium holds roughly 100 billion solar masses of gas. Let that sink in for a second. There is actually more baryonic matter, normal everyday matter, in this hot halo than in the entire compact, cooler galactic disk itself. In fact, finding this hot gas was a huge deal because it helped astronomers solve the famous missing baryons problem of the entire universe. It acts as the primary building material for future star formation in the disk. And it's not just sitting there quietly either.
Our galactic halo is an incredibly dynamic environment. The vast gravity of the halo actually dictates the orbits of satellite galaxies, like the Large Magellanic Cloud, which is currently flying by at a whopping 40 kilometers per second. As it passes, it gravitationally pulls the Milky Way's cold disk toward it. This process physically compresses the hot gas at the bottom of the halo, kind of like a piston in a car engine, which heats the material up by an unbelievable 13 to 20%. So the halo is very much an active, evolving space. Which brings us to Section 3, Relics of Galactic Cannibalism.
Let's look at how this whole thing was built. The halo formed through what scientists call hierarchical cold dark matter assembly, which basically means it's a bottom-up process. In the very early universe, small dark matter and baryonic halos formed first. Then, these small pieces violently crashed and merged together into massive groups. During these huge collisions, the gas cooled and flowed inward to forge the central disk that we actually live in today. But what about the stars and dark matter from those consumed galaxies? They didn't make it to the center. They were left behind, stranded out there in the extended galactic halo.
And the amazing part is, we can literally read this history like a cosmic fossil record. About 13 billion years ago, the infant Milky Way started throwing itself together. Then, at least 12 billion years ago, two primordial pieces, which astronomers recently named Shiva and Shakti, were fully absorbed. Later on, around 10 billion years ago, a massive collision known as the Gaia-Sausage-Enceladus merger scattered a huge population of blue stars deep into our halo. 10 million. That is the mass, in suns, of the newly discovered Shiva and Shakti star streams. These ancient stellar streams are direct evidence of galactic cannibalism. They're the literal fossil remains of galaxies consumed billions of years ago. These specific threads sit about 26,000 light-years out from the galactic center. And what makes them so absolutely fascinating is that they send astronomers really puzzling mixed chemical signals. They lack iron, which strongly hints they were born outside our galaxy, but they are incredibly rich in other heavy elements that we usually attribute to stars born locally inside the Milky Way. It's a total cosmic mystery, and scientists are passionately debating it as we speak.
All right, moving on to Section 4, the dark matter scaffold. This brilliantly illustrates just how much dark matter dominates the big picture. Dark matter makes up roughly 84% of the mass energy density of the universe, while the baryonic matter, the normal stuff making up stars, gas, planets, and us, is just a measly 16%. In the context of our halo, dark matter absolutely rules the gravitational pull. It completely dictates the overall structure and behavior of the entire galaxy. And because the halo is so massive and heavily dominated by dark matter, studying it might just be the skeleton key to finally solving the universal mystery of what dark matter actually is. But, as it turns out, this invisible scaffold isn't perfectly round.
Actually, recent radial profile analyses have revealed something astonishing. The dark matter halo is twisted. In the inner regions, up to about 20 kiloparsecs from the center, it aligns perfectly well with our flat stellar disk. But as you move out into the deep edges of the outer halo, the dark matter structure literally flips on its side into a vertical, perpendicular orientation. So the entire framework of our galaxy is structurally warped. How wild is that?
Finally, we reach Section 5, decoding the Milky Way.
So, how are astronomers actually putting this giant puzzle together? They're using some incredible tools for what they call galactic archaeology. First up is the European Space Agency's Gaia spacecraft. Gaia is out there mapping the exact motions, ages, and spectra of billions of faint stars. It's basically giving us a sharper pair of glasses every single year so we can see the halo's incredibly slow rotation. Then we rely on supercomputer models, like the Auriga suite. This runs hydrodynamical simulations of 25 Milky Way-like galaxies over billions of years, just to see how these halos naturally evolve. And finally, astronomers can study our halo's hot gas by analyzing the light from distant quasars as it passes straight through the circumgalactic medium, relying on powerful tools like Hubble, the James Webb Space Telescope, and advanced X-ray observatories.
So the crucial takeaway here is perfectly captured by astronomer Bob Benjamin. Every galaxy has its own unique story, but what's special about our galaxy is we can put its story together. That's really the heart of it. Because we live inside it, the Milky Way is the ultimate testbed for understanding the universe. We can literally map individual stars that have been orbiting in the dark for 13 billion years.
As missions like Gaia continue to send back absolute mountains of data, and as future powerhouses like the Vera C. Rubin Observatory, the Nancy Grace Roman Space Telescope, and the Square Kilometer Array all come online, we really have to ask ourselves, what other invisible ancient fossils are still hiding out there in the dark reaches of our galactic halo? The true story of our galaxy's violent, chaotic assembly is really only just beginning to be told. Thank you so much for joining me to explore this invisible sphere around us. Keep looking up and keep asking questions.